Yeah, perfect. Okay. So our next speaker will be Lin Shao. He's professor at National University of Singapore, and I think he's going to talk about manipulation using differentiable simulation.
Oh, hi everyone. Thanks for the invitation, introduction. I'm Lin from National University of Singapore. So my main field is about robotic manipulations. Title of my talk would be large-scale manipulation data acquisition through differentiable physics simulation and rendering. And like everyone's right now talking about the data, I mean, it's plays a crucial role if we want to move next step towards the build the foundation model of robots. When we're talking about the data, right now there's one of the resources is from online videos, right? Definitely will provide this data resources. And based on top of this data, there also is researchers already been developed learning from demonstrations that can significantly reduce the need for the reward engineering. And also this kind of data also has the potential to broad this skill acquisitions, which may has the potential to lead to the foundation model for robots. And when we're talking about utilize this large source of data, actually challenges immediate rise because the largest data formats that are available online right now is simply RGB videos. I mean, only RGB videos, not depth. There's no object shapes. There's no camera poses. That's make it hard when we're talking about how we're going to make full use of this, especially for robotic manipulation because it's more about the spatial relationships and interaction. And next thing is there are no specific task reward and how we are going to learn this. It will become crucially important thing. Another thing is, although the total amount of online videos is pretty large, but when we're talking about dividing into specific tasks, actually the numbers are actually limited. For example, I'm going to talk about learning how to knot a tie. I don't think there's many online videos that specifically tackle these problems. And to mitigate this, actually, we probably want to consider reconstruct and estimate this 60 object poses, so that we have a potential to transform every single RGB videos into 3Ds. Right? And for this task-specific reward, we also consider maybe we already have object 60 poses as sub goals. This kind of provide ways to describe what the specific task should be done. Right? When I'm talking about 60 poses, I'm also talking about more general things. It's about for deformed objects, it's about object shapes, not only the 60 poses. And once this is there, actually, we probably want to consider how we're going to utilize the model-based learning from demonstration, leverage differential simulation and rendering. Right? But one thing we want to mention is although there are a lot of data already there, but I really want to ask the question is what kind of information or knowledge we're expected to gather from this online videos. Or just do this end-to-end fashions that would be leveraged, that would be useful for purpose robotic manipulations. Definitely that would be one possible ways. But I really want to talk about another potential, which is how we're going to frame the structures in terms of robotic manipulations. All right. Generally, we consider my personal would prefer we have hierarchical one. Generally, we are going to have two levels, 5 levels. For example, once we have instruction, once we have image as input, we hope we have a high-level manipulation planners that kind of plan the task ahead, right? It tells us how the task should be done, no matter what kind of robot it is involved, right? This kind of plans tell us, okay, so in order to finish a task, what kind of object shapes or changes should be made. And once the task is there, which we probably able to transform from high-level tiny task level to low-level manipulation, models. There we can have robots, to insert, to perform and manipulate the objects to follow the plans. Right? That would be one thing. And of course, definitely the framework should be generalized across different objects, robots, and tasks. So following this, I'm talking about several related works. But for this talk, I'm going to focus our model-based learning from demonstrations. And the one of the advantage was we are also hoping that we have learning from demonstration method that could work for dexterous hand, especially dexterous manipulations. These are super challenging if we consider how we're going to learn it from demonstration. And also we're talking about a shape, a reconstruction, and also model-based manipulation policies. Once it's there, we are hoping that we could have a behavior cloning and run RLs when we deploy it in the real robots. So this would be like a general overview of the one of the works, so-called deep learning from demonstrations. So generally, the idea is like this: when given like a human demonstration that only has RGB videos, so we are hoping to have like a perception model that could do shape reconstruction estimation, right? Given these videos, we hope that we will be able to leverage the differential physics, differentiable rendering, that kind of estimates reconstruct shape. And it's also like the shape, the change of the shape and the poses actually self-indicating what exactly the task. Right? That is like object-centric views. It's only talking about if the task, what exactly is the task itself. Right? It's indicating the change of the shapes or the object. And once it's there, we are trying to like transform it from like the high level object-centric view to like a robot-centric view. It's like we already know that from the videos, we know that we have estimated the shape and the poses. We know that what kind of like sub goals we need to be able to achieve. Then the question becomes like how are we going to control the robot, how to output the actions so that the robot could manipulate and interact with the object to transform its shapes. All right, and this will be usually loaded into simulations. Then we're going to calculate in what kind of force and torque, what kind of areas of like the robot should make in contact with the object, so that it will follow the planes. And of course, after this, everything is in the simulation. Definitely, we will consider doing it in the real world. But sim to real is always something that we have to face, we have to consider. So right now, our plan was we will have to do this like a behavior cloning. We're trying to do like a teacher and student policies to transform the knowledge into a neural networks. I personally, I don't think this is necessary, but as long as the simulation should be fast enough, we should be able to fit the simulation in the learning loop. But so far, especially for complicated manipulation or dexterous manipulations, these are there's still like a lot of effort need to be done. But one thing I want to mention is like although it is still like a manipulation of dexterous hand, but one thing is different is now the robot itself actually is holding it, right? Holding it with the fingers, right? This would add significant effort to the like task difficulties instead of have palm supported. Right? Which means that a small tolerance, it will result in very small tolerance. So as small distance or small disturbances may directly result in the failures of the objects that fall into the palms. So I'm going to go through one part by part. So this would be like a shape and a pose estimation pipeline. So assume that we have a video demonstration. Human beings is manipulating the tip, rotate the tip. What we want to do is we are going to have like a two-stage estimations. The first one, we're going to leverage the differentiable simulation. We are going to reconstruct the shape and the textures, and also estimate the object poses. Right? As I said, this changes of the poses indicating what task indicating the task itself is indicating in order to achieve the task, what kind of object change and object shape or poses should be achieved. That be recognized a success of the task. Right? But one thing to mention is like when we're talking about learning from demonstrations, like the viewpoints is always something that we need to take consider because like most of the videos we only have like single views. Like when we do like a reconstruction, we probably want to leverage. There will be always like a partially observable and occlusion of the object, which means that we are kind of need to introduce like more resources to finish and predict the invisible part. So right now we are leverage. So this will be like second stage. We are trying to do like a reconstruction and leverage electron knowledge and prior knowledge to improve the reconstruction of the shape. All right. So first one is the ways to estimate the shape and the poses. First, the thing we are going to do is we're going to have like a mesh initialization. All right, we start with something that has simple geometries, and then we're going to like the scaling the shapes and the pose of shapes to match the contour of the object. Right, and once there, we're going to have like a shape optimization. We're trying to add small things on top of that to match the contours of the object. And once this there, we're going to have like a texture optimizations. The great part about this differentiable rendering is everything can be done in the like a gradient-based optimization, so that we're going to gradually match the observations. And once the texture is there, we're going to have is like a pose estimation. So I want to mention this like we are trying to do this in this way. It's like a self-supervised manner. It's have what you just based on what you have. Render image, leverage the differential rendering. Compare the rendered image with the real world demonstrations. Right? Compare the difference, it has a lot of type of algorithm back again. Finish the loop. And through that, we should be able to simultaneously generate the meshes and also the poses in a self-supervised manner. So far, no learning involved yet. And then one thing we want to mention is like usually the occlusions, the self-occlusions. So what we want to do is we're going to, in this work, actually, we're going to leverage the large models. For example, we have diffusion model that would be able to generate synthesized novel views that hasn't been appeared in the demonstration video. So with this, we're going to have like a more images that are taken from another views so that we'll have like full shape. Then finish this reconstruction. This will be like a area refinement. Yeah. So these two kind of faces are doing iteratively until some like convergence is maintained, right? So I really like this because this works in the self-supervised manners. We're able to reconstruct or estimate or track what would happen in the online views. Once it's there, we assume that we should have like a detailed shape and also like estimated poses. So now everything will be loaded into the simulation since we already have the shapes. The question now becomes, oh, okay, well, I don't know what specific task it is because like we already constructed the K-frames that they already illustrate in the videos. The next thing for robotic manipulation research to think about is what kind of forces, all right, should be insert or manipulated towards the object so that will follow the poses. Again, so this will be like the estimation result. So we are formulating this like a content-aware manipulation policy as like a graph search. Right? The node will be each of the node will represent the object contact point and also is associated 60 poses. That's the definition of a node, but we're also going to have like edges. This edge is actually associated with two manipulation primitives. One would call it like contact localizations. Contact localizations is trying to say like, okay, we need to figure out which contact, this is basically trying to select the point of contact set that enables the fingers to make contact with the object so that there will be possible forces that can be applied, force and torques that can be applied on object to rotate or manipulate and change the shapes towards the target tool. Once we have this like contact, we should switch to this like a contact range optimizations. Basically, we're trying to optimize the simulations, optimize for the contact ranges in the differentiable physics simulations. The first one would be the contact point localization. Since right now we already make assumption that based on this previous learning from demonstration pipelines, we already have estimated the 3D shapes and also its corresponding like 60 poses at each time frame. Now we're going to based on this like current like object 60 poses and also the estimated 60 poses at the next frame, we should be able to calculating the transition ranges. Basically, what kind of ranges the object should receive to transform it from its current pose to the next pose, right? And once we have the pose, the question will be, find the contact points, a set of contact points given the number of the fingers that should be able to produce the object transition ranges. Right now, this part is like we observe that sampling based method should already work quite well. Mainly because there will be a lot of there will be multiple solutions. Once we are going to sample one, we should be able to start from that and try to iterate it. And then we're going to transform from this like contact localization to object range optimization. Basically, we're going to since we already know the contact points, we're trying to not break the contact at this point. So we're going to like optimize the force and torques that that will transform the object poses towards this target pose. Also with the penalized on the velocity of the poses and also the magnitude of the ranges. The good part about this is everything right now is done in the differential simulations, which provides a gradient for us to do this. But you you're probably already aware that for contact for manipulation, especially contact-rich manipulations, the gradients are usually hard to calculate in, and also there's some discontinuities. So what we do is we're going to leverage some a smooth gradient. Basically, we are trying to have some perturbation that trying to have estimation of the gradient. To deal with this incontinuities. Basically, we're trying to solve the step function of discontinuity functions. So with this, we'll observe that we should be able to quickly calculating the range that's needed to transform the object from its current pose to the next pose and then iteratively do this. All right. And with this, we're able to finish this like a manipulation model-based manipulation policy search. So this is really great that is we're able to support this textual kind of manipulations. And it turned out that it works quite well, mainly because of the hierarchical things, right? I mean, generally the gradient-based algorithm that can easily stack into local minimums. With this, actually, we are trying to divide it in two parts. Because the first one is we have global search that is trying to determine what would be the feasible contact points, right? And once we have identified some of the contact points, we're going to optimize this the ranges in the local way. So this is a kind of hierarchical combinations that kind of play a crucial role, trying to mitigate the potential to get stuck in the local minimums. So with this, we are able to find the manipulation policies in the simulations. Right. So far, we have talked about given the demonstrated reduce, we want to leverage the different renderings to estimate the object shape and also associated poses. This represents the task itself from the object-centric viewpoint. And then we're talking about, okay, everything is now responsible for constructing a mesh. We should be able to load it in the simulations. Now the stage is transformed from the object-centric views to robot-centric. It kind of forces the robot to exert towards the object so that we will follow the previous estimates of objects sequences. Now the next thing becomes okay, everything is done in the simulation. We are actually interested in how we're going to transform the knowledge discovered in the real world. So far, what we do is we're going to utilize the trajectory that we are generating in simulations and render it and fit this into the neural network stuff. So basically, we are going to do a behavior cloning that finish that we will learn closure policies that's trying to do this real world. In the process, we also need to fine tune a little bit with the reinforcement learning so that to deal with the sim-to-real gap. Right. As I mentioned, I really hope that the simulation itself could directly apply into this learning loops so that really we can get rid of this neural network stuff. But for the state estimation and the dynamic calculations are still require some effort. But I think if the differentiable simulation, all the state estimation and the simulation calculation should be fast enough, this may be a possible ways. Because once there is everything we have demonstrations, everything we plan in the simulation could be directly guided. We can do closed loop online simulation calculation that guide the robot to play, the actions and the manipulation. This will be super cool. All right. So this will be the general overviews about our learning from demonstrations, which we are hoping that we are able to guide the robot to to learn this skill that already embedded in the large scale videos that are available online. One thing we were starting to jump about, okay, how good it is. We're going to evaluate each of the components. One thing is compare the shape of our reconstructions. We currently compare with the nerves. So what we did is we're going to have input of the mask, and we're going to say okay, based on the differential rendering and also the self-supervised shape reconstruction estimations, how good our pipeline is. It turned out that this a simple strategies actually can work very well. It's dealing with a larger variety of tasks. Some of the really challenging one we did a watch because of the complicated shapes. Our methods will be able to generate very good a shape, and also a hamlet. So everything, this is, once I mentioned this, you probably already see like this similar performances from like the 3D foundation shape reconstruction. But I want to mention these are directly pure from optimization strategies. And we also compare with like a nerve. Turn out like a nerve does not work very well in these cases. You see like some of this will be like a fog stuff that are making it look like unrealistic. And one thing is because like in the demonstrations, like we in like in the typical nerve setting is like we have like a static object. Then we're going to do like a one circle, like a filming. That will finish like the 3D scan of the shape. But in the online videos, usually it's not the case. You just have one fixed camera that look on the manipulation steps. Right? It's extremely challenging to have the chances to get around these videos. And that is like one of the challenging part of our nerve. One thing is about like an estimation because our input will be a masked video. That will make it a challenge since like a structure, like the nerve, it's hard to for nerve to capture the relative poses without the background. All right. And then we're talking about like diffusion models, right? One thing I mentioned is like for these online videos, most of them lack the global or the full viewpoints. So our strategy would be we leverage them like diffusion models to synthesize the views that happen appear in the videos, right? And it turned out that like with this way, we should be able to significantly improve the shape estimation in the invisible part. So this line is indicating that if there's no like a diffusion, if there's no diffusion synthesized models, this will look good. It looks reasonable on this visible part that already appeared in the videos. But it's become extremely challenging to estimate these like invisible areas, right? And the very last line is indicating that with the diffusion model, we're able to restrict the shapes so that it looks in a reasonable manner. And then we started talking about like how we're going to compare with like other planar masters, like for this, there will be like a bunch of like a baselines. There will be ILQR, RT search. It turned out that like our combination between this like a pose and also the contact point in a global global search the contact point and do this local range optimizations achieves like a reasonable balances between the computation time and also the reconstruction measures. The reconstruct the estimate the differences between the poses and the target poses, right? So we have this range that we have achieved like the smallest like a minimum square error with a purely very short like computation times. This is very exciting. That's why I'm thinking like whether they maybe have chances that we can directly plug a simulation into this like the robot execution network. All right, and we also compare with the RLs. It turned out that definitely we will have like a more requires much more less training time, but compared to RL, if we do purely to RL, we will have like time less training times. And one thing to mention is like since everything is like projected we'll do like a behavior cloning to train on like a policies network that's kind of provides some generalization to new object. Meanwhile, we also deploy into the real world. This is one of the things that we really need to consider if we plug the simulation into learning loops because generalization becomes super hard. But for neural networks, like these interactive structures already give some interpolations about the generalization possibilities. All right, this will be the experiment about the RL. All right, just like a brief summary. So we're talking about the learning from demonstration pipelines. We hope that we could have like a directly estimate, compare fashion that could do this in a self-supervised manner that we could deal with larger number of videos that we can extract the knowledge and reconstruct it and make a digital twins and be able to transform this digital twins and knowledge to a real world. All right, that will be the things. And again, so previously we were talking about the rigid part estimation. The rigid part estimation for differentiable simulation is still okay. Now we are trying to push the limit to consider like whether we can be applying this like a pipeline to do like a more challenging task, for example, closed manipulations, because of the high dimension, high DOF. Right, the closed manipulation is just like everyday activities. So there will already be like a bunch of like closed manipulation tasks that are mainly about the folding and unfolding t-shirt. These are kind of easy to implement because they're easy to design reward for the RLs, and all those actions are actually associated with simple grasp and move or grasp and pick and place actions. And to collect this, make it easy for robot collection at low cost. Some of the related words, for example, speeding, folding, and flipping bots are there. But like we are trying to see like whether like this kind of digital twin, this learning from the like a real world can be the knowledge is leveraged from the real world can be directly leveraged to do more challenging tasks, which is time knowledge. Right? So how to solve like a closed manipulation that involves complex object shapes and requires like non-trivial actions and difficult to collect data. So time knotting task actually is extremely challenging because it requires sequence of actions. To be honest, I don't know how to knot time. So that's also the motivation. Say, okay, if we have like a pipeline that could learn how like train a robot or teach a robot how to watch the human demonstration and then be able to knot time, that would be super cool. And then also kind of like a testing what would be the boundaries of current technologies. So time knotting task is actually extremely challenging. One of the reasons is about the like the complex like the topologies. It's like to be honest, I'm still cannot figure out what will be the changes. Even I watch the videos. And another challenging was, but like if we want a robot to learn how to knot a tie, we have to have a way to robot itself to understand the reference topology changes. Although I don't know what's the math behind of it, but I still have a way for a robot to infer. So that would be one challenge. The other challenge is about like object trajectories. Like in the processes, the shape. Now I'm not talking about like in the object poses, 60 poses. I'm talking about object shapes, right? Because in the previous demonstration, I'm just doing like the rotation. I'm trying to learn this, like learning from demonstration ways. We infer the object poses. But when we're trying to learn not a tie, the poses actually are become a more standard, more broad concept. Is like a general shape, right? And this means that we need to have a way to estimate the reconstruct object shape sequentially. So that would be like one of the challenging part. So again, we're going to follow the pipelines in doing in the real to sim to real, learning from demonstration pipelines. Basically, the idea would be we have demonstration videos. We hope that we could have like sim to real gap that learn the object shape from this like a simulation, right? The object shape itself, this would represent like the change of shape itself represent how a tie should be knot, right? And once we learn it, we're able to transform this into the real world. So this would be the general pipelines. And again, I want to bring this like the slices back again. I want to emphasize if we want to do this knowledge transfer, we have to identify what exactly knowledge robot need, right? Okay. So this will be like the general idea. So we hope to have plans that learn from the demonstrations. And again, this learning from demonstration parliament should be able to mitigate these things. One thing I want to mention is about the difficulties that we have developed in our groups. Due to time limit, I'm going to skip this part. Let's say we are going to have like simulations that are going to preserve or maintain the intersection properties during the time knotting tasks. And with this, we were able to, like estimate the 3D shapes. The really challenging part is how we're going to, like link the differences between the shapes. One thing is also about the insurance topologies. This cool part about this is using the physics simulation to pose this object constraints between like one frame, one shape to another shape. Okay, with this, we should be able to maintain this. I guess one of the challenging points that are appeared in this time loading task is how we're going to, track the differences between one frame and another frame. Okay, that would be one of the main part. So what we did was we're going to have ship matchings that are trying to, track the differences between each of the pixels across different frames, right? However, this generally provides a good ways, but it also sucks if, for example, one part is of the ties disappeared or totally invisible. That's why we were going to have a global orientation, the key point prediction that are going to finish play anchor points, even though some of the meshes or part of the meshes is occluded. Together, we are able to have a way to link this shape ties across different time steps. And with this, we should be able to use this a match information between two frames to guide the simulations. So we're going to have control points that we predefined that are going to that we assume that on the mesh on the time end that the simulation the real world is already aligned. Then we're able to optimize the control point and the meshes that to match towards this image. Use the differential simulation. That will be the general timelines. And also there will be learning app simulations. We're going to reconstruct the times in the simulation. Then the next question would be, we need to identify where to grasp and where to pull for the robots. This is down in the RL fashion. We're trying to given the target match, we're trying to decide what would be the possible candidate to grasp. And then we're able to decide what would be after we select the target grasping point, we're going to identify what would be the termination or the strategies.
Can we just slowly wrap up?
Sure.
Maybe one more slide.
Good. Yeah. So with that, we should be finished this teacher policy. Previously we calculate everything in the teacher policy. Now we are going to transform it into student policies. We're going to render this the meshing to the point count. This would mimic the real sensors that we have in the real world, right? And this will be the general result. This will be the real world simulations, the real world executions, right? So just to wrap up, so far I'm talking about how we're going to leverage the differential simulation and renderings that we are able to enable the robot to learn from these online videos that are going to transform all these knowledges that are embedded in the videos into robust skills, right? All right. Yeah, thank you so much.